What's up, y'all? Okay, so here's the deal. This particular lab is going to be a steam distillation, and we are essentially extracting essential oils. And so I know you know about essential oils because I know you love them, right? Little drop into your humidifier or whatnot. I don't know, like eucalyptus, lavender, some other essential oil that people like. I don't really know essential oils. I just know about lavender and maybe eucalyptus is a thing. But yeah, you can essentially isolate those oils with this steam distillation process. And so, in short, what are we doing? Well, we're combining water and cloves, ground up cloves, into a round bottom flask. We will heat that round bottom flask, and the oil from the cloves as well as the water will co-distill. We will isolate them as a co-distillate, and then we'll separate the oil with methylene chloride because the oil is it is nonpolar and is soluble in methylene chloride. Methylene chloride can then be easily boiled off because it's got such a low boiling point, and then we can have our more or less pure or clean essential oil from cloves. Really cool process. Okay, so why do we want to do it this way? Like why can't we isolate it some other way? Well, steam distillations are awesome because they allow you to isolate high boiling point substances, but using relatively mild methods. So water, not a toxic substance. So that's perfect to use in an organic chemistry lab. And then it allows us to heat them at a mild temperature as well. So, and that's because the reason why that's important is because if we heat at a really high temperature, then we risk decomposing our substances. Okay, so that's one of the reasons why steam distillations are so good and useful, is because we can heat at milder temperatures and isolate those natural substances, but without the risk of decomposition or maybe like reacting as well. So in addition to that, so like that's the why. Now what's actually happening, right? So what's going on is when you combine two immiscible liquids, you have a depression in the boiling point of the mixture of those two. So for example, if we mix 100-degree water with 200-degree something else, oil, then the mixture together will not boil at 100 degrees, nor will it boil at 200. It'll actually boil lower than water, which is the main component. That's why. So let's say it would boil at like maybe 90 or 95. Okay, so that's why this is awesome, because we can heat at a mild temperature. Okay, this is different than this concept is important because if you mix two miscible liquids, the boiling point is basically, let me slow down real quick. Slow down. So for two miscible liquids, you combine those two together, and the partial pressure of one substance and the other is dependent on the concentration of those two, so like the amount of each substance. Whereas in a mixture of two immiscible liquids, it's not dependent on the concentration of A or B, for example, or the water and the oil. It's that's because they're really not. You can think of them as not interacting with one another because they are two separate things, because they are not miscible, right? There's two layers, and so what happens is as you heat it up, you get some of them going into the vapor phase, and it's equal oil and equal water, consistent oil concentration in the vapor phase and consistent water in the vapor phase, concentration of water in the vapor phase throughout the whole distillation. It doesn't matter that we're losing or lowering the concentration of oil in the boiling flask, okay? Whereas that does change things up when you're boiling miscible liquids, okay? Now, Why does this matter? Well, it just makes it easier to kind of steam these things off. The the boiling point, basically what happens is we have vapor phase of the two liquids, so oil and water, and then they cruise on over to where it collects and it condenses into a liquid, and then we isolate that. Okay, so that's pretty much a distillation, right? We've done this before, but I like to think of it as like every liquid has a vapor pressure, right? So every liquid has a vapor pressure. Even like mercury, super dense liquid, mercury does have a vapor pressure because it is a liquid, right? And so just imagine some of that vapor from the oil and the water coming up, and then they kind of just mix together and they float off together. Okay, that's really what's going on here. The reason why this works at lower temperature is just because when you mix them together, the boiling point overall lowers. So it's lowering for everything, right? And that's what makes this so cool, so useful, so essential. I don't like using the word essential when I'm talking about essential oils, but I mean, whatever, you get it. So basically what happens after we isolate that co-distillate, we have water and oil mixed together, and then we'll throw a little methylene chloride in there, extract it out, and then boil off methylene chloride, and then we've got our cloves oil, and then we will be able to take an IR of it, see what we got there. Okay, so we should be able to identify the functional groups in the IR and analyze that. In addition to that, obviously the errors and things like that associated with the experiment. Definitely some errors in here, so keep your eye out. Super fun. Literally the best smelling lab, and you're missing out on it. Super bummer, right? But maybe next time. Just sniff some apple pie or pumpkin pie. I do want to add one last thing. Sorry. So the relative ratios of water to your substance, like clove oil in this case, it will be consistent throughout, because again the vapor pressure is consistent throughout. The partial pressures of each liquid is consistent throughout, and the ratios can be determined as long as we know the partial pressure of each of those given liquids at the specific temperature that we're boiling it at. But we don't know that for this one, and so that's why we're not necessarily determining the relative ratios. But for example, if we did know that the partial pressures of water at 95 degrees and then clove oil at 95 degrees, then we would very easily be able to find that the relative ratio. And so let's say it was like 90% water and 10% oil. Like that's useful information. But then also I do want to point out, the larger the difference between the boiling points of pure water and pure oil, the larger the amount of water that will be present, which makes sense, right? Because we're only heating it at basically water's boiling point, right? So for example, if your boiling point of water is 100 and your boiling point of your oil is 200, then we might have like 90 or 95% water and then 5 to 10% of the oil in that distillate, okay? But if they're both around 100, then you might have like a 50-50 mixture or something, maybe even better than that, like 60-40 or something. But so anything in between or higher, then you'll get a similar result, or that trend will follow. Okay, so just wanted to add that to it. Okay, how's it going? So here we go. What I have is my round bottom. I got my Hickman still head and my water jacketed condenser, right? So the first thing I'm doing is, actually all I did so far was weigh out 1.172 grams of cloves, and then I shall pour it into here. Okay, write that down, 1.172 Uh-huh. 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 1.172 grams in this round bottom. And what you want is around 12 to 15 milliliters of water, and you're gonna let it soak for 15 minutes. So when it says 12 to 15, that means 12 to 15, somewhere in between there. So what I did was I poured 11 and some change in there, and it doesn't have to be perfect is really what I'm getting at. You just need some water in here. And we're gonna let that hang out just to kind of get these cells kind of bursting with, so we can get the access to that oil. Okay, so I'm going to go ahead and clamp this. Here, check it out. Check it out. All I've done is just clamp it right here for you, and I'm gonna walk away from it. Okay, we'll come back to it. I'll probably come give it a little swirl every once in a while because I know not all of those cloves are wet, but that's it. All right, so this guy's been chilling for, I don't know, I honestly don't know, 15, 20 minutes. That's one of the benefits I have of doing this, is I don't have to be out in a specific amount of time, but what you wanted to do is let that soak for 15 minutes just to ensure that all of the cloves get wet. Now what we want to do is add some boiling stones. Just 1 or 2 will suffice. Well, not a million. I know a lot of people, when they see these, they're really tiny rocks, essentially. Let's see if you can see those. Yeah, kind of. Maybe you can see, maybe you can't. They're little tiny rocks. So I'll add 1, 2, and what this does is, I think we mentioned it before, but doesn't hurt to mention it again. Get that jammed into your brain. What it does is it kind of there's bubbles start to form from these little rocks. They're really porous. And as it's heating, those bubbles kind of disturb the surface of the heating water. And so that allows, when those bubbles are created, the disturbance allows it to kind of just be bubbling, right? As opposed to almost like just keeping like a nice seal almost, because water's got some strong hydrogen bonding. And then eventually when you heat it up so much, it eventually just kind of pops and it kind of explodes. And we call that bumping. And so what can happen if you don't have your boiling stone inside of here is once this is all together like this, let me get this guy out. Once this is like this, if it splashes inside of this, like if it bumps and explodes, some of those cloves will end up getting up in here, and we don't want that. We want just the distillate, so the oil as well as the water to distill up in here. We want them to co-distill in here, and then we're going to collect it. We don't want to collect solid material, so if that does happen, we're going to have to rinse it out. It's possible. Sometimes it happens, even when we are really careful, and that's okay. It's just kind of the way she goes. So while I was waiting for that to soak, I went ahead and filled up this thing right here that you can't see. I'll get you another one to show you, but I filled it up. It's basically a sand bath. And it's got this power mite here that allows me to regulate the temperature. And the goal essentially is to make sure that we are heating at a decent rate to get this distillate to collect I don't know, like 2 to 5 drops a minute or so. We eventually want to get to about 8 mils of distillate collected into our what is that? Centrifuge tube, because then we're going to extract it and then we're going to move on with our life, right? But for now, this is the setup. You've seen the setup before, but what we need to do is we need to put water going in the bottom of our water condenser and then out the top. The reason for this is because if you have hot vapors traveling up this, where are they the hottest? Well, they're going to be the hottest at the bottom, right? So you want the coldest water to come in and cool that off, and then peace out, get away the warm water, and then circulate through. It's also going to allow it to actually fill up completely, because if you fill up through the top, gravity will take control of this one and it'll just flow out faster than you can put it in. And and it's not gonna fill up. It'll fill like halfway up, and you won't get the whole condenser cooled like you want it to, because you want it maximum cooling to ensure that we don't get a loss of any of our materials. So the co-distillate, so like the oil as well as the water, we don't want that much. We don't want it to leave. Okay, so let's go ahead and get that water tube on there. All right, so before we heat that bad boy up, we're gonna connect this tube, the other end of this tube, into a faucet. That's gonna be water in the bottom. Okay, put that on there. And then I have another tube that I'm going to connect here. And cool thing about, I mean, you don't, it's very straightforward. So there's not much to mention about this, and you don't really need to see the faucet, but it's just connected to a portion that looks like this on the faucet. And you just want to make sure that it's on there well enough so that way it doesn't pop off when you're in the middle of the distillation and get water all over everything. I've seen a lot of lab notebooks get real moist. So let's see if we can secure this well. I use this one pretty much the only one I could find it right now, but this happens to be a really long one, which is ideal because we're not going to strain the tube to make sure we can get the right, like any angles, so that we're tugging on any of these portions right here to force them to pop off. We don't want that to happen. And so one thing you also want to make sure you're doing is turning on the water very slowly. And you'll be able to see this fill up, okay? Now we don't need a crazy flow because we do have to keep it on the whole time, and we don't want to waste too much water, right? So what you can do is hold, let's see if I can get this guy to start draining. So on the other end right here, you can see it kind of trickling down, right? And so that is a decent water flow, because we definitely have it moving, but it's not too much that we're just gonna use all the water ever, right? So I think that's a great start right there. So what I'm gonna do is, since I've got everything kind of on there and secure, I will go ahead and lower this into the sand bath and then take a look at the solution to see how that is boiling. If it's not boiling, then we can adjust the temperature on the power mite here if necessary. One thing I do want to kind of make note of is that this edge right here, or not edge, but this joint right here, it can very easily come off right here. So you can seal that oftentimes in a laboratory with Teflon tape. We don't have Teflon tape, so what I'm going to do is place a clamp there for you. Here, let me just grab that. And since these are the small pieces of glassware, it's the yellow one, the small one, and you want to make sure that you connect it so that the larger circumference is going around the larger portion of the joint. So the bottom portion is going to be right there, and boom, we got that click. And so although these are not perfect, they do help, right? So we want to make sure that we have them as a backup but not depend on them. So I would never like disconnect this and then hold it from here without having anything under my round bottom, because now you're just being ridiculous. Okay, so let's go ahead and lower this into the heat, and then we'll check on it. Okay, so I'll be back. All right, so here's my setup. Ain't it pretty? So notice I have the sand actually covering a good amount of my round bottom, because I want to make sure that I heat not just the liquid in the round bottom, but the glass above it, to ensure like proper heating, or like the most efficient heating as possible. Because those vapors that go up, we want them to go up and not cool down, not just yet, right? We want them to heat all the way up into here and then cool down and collect on this little well right here. You see how it's kind of like curved down? That's what we want to collect it on. and I'll show you how I gather that material when it comes time. This joint right here, I don't personally feel the need to clamp it or even seal it. I just need to make sure that it's nice and snug. You always want to make sure you're keeping an eye on the water. The water level you can see is right here. You can see some movement. You can keep an eye for bubbles to see if there are any going up, like due to water flow, but you can also take a look at your sink and just kind of hold this up to see if we have water dripping. Okay, that means that the water's on and it's all good. Okay, so I'm gonna let that hang out for a minute to see. Just keep an eye on this area to see if I get any action. If I don't see any bubbling, then I'll likely increase the heat on my power mic. Okay. All right, so if you're anything like me, look at that. We got a little bit of action here. There's some vapors. I put a little foil tent around this because a lot of that heat we're kind of losing to the environment, like the lab, right? And so what I did was I just kind of wrapped it around there. One thing, you kind of just wrap it around there. You can make a little slit in the foil and then keep it kind of connected in the back. That way you can wrap it around there more easily. So I want to make sure that we're collecting this at a rate of about 2 to 5 drops, or I'm sorry, like a drop every 2 to 5 seconds. Okay, 1 drop every 2 to 5 seconds, and just basically just don't get too crazy. That looks pretty good. I like it. I'm loving it. I'm wanting some more of it. So what we're gonna do is we're gonna have to collect now. And one of the things, we'll see how it goes, but we might have to kind of bend this guy, but I'll show you when we try. So I'm gonna let that well fill up, this guy right here, as much as possible so that it doesn't overflow, and then we'll go ahead and collect it, okay? All right, so this is perfect because we got a little bit of bumping going on in here, right? So that kind of means that the heat was a little bit too high, and so I took the foil off. We can also, what we always want to do, and anytime we have something heating, is we want to keep an eye up here, just to make sure that our condenser is doing its job. If we see any vapors up in this area, more than halfway really, then we want to make sure that we probably turn that temperature down. But I don't think we got really anything that was necessarily, we didn't get any solid material inside of this well, so that's good. But what we can do is go ahead and collect that in a second because it looks like it's overflowing now, possibly. I kind of want it to overflow a little bit just to rinse any of that solid material down. Okay, let's give it a little bit less heat, probably, so we can have that bad boy simmer down, simmer down, simmer down. Relax. All right, I'm gonna open this, and oh yeah, look at that. See, check that out. We got nice and brown in there, so that's not good, right? So that means our temperature was a little bit too high, which is not uncommon, especially with these sand baths. So what we want to do is try and I could raise it out, and I should have done that first, but I also wanted to show you what can happen, right? So let's raise this now. Go boom. Okay. Now let's go with now. Let's go ahead and oh, it smells so good. I'm in the Thanksgiving spirit for sure already. I don't know about you guys, but love Thanksgiving. I just love food, I think. So, yep, food and family. Unfortunately, it's all about food this year. Not so much family, just the immediate family. So what we want to do now is we'll go ahead and spray some DI water along this, allow it to drain back into here, which is totally fine. And then we'll go ahead and continue the process. So when I do this, I don't want to get too crazy because I don't want too much water in there. Otherwise, it's going to cool down everything, but it's also going to fill up that round bottom. And if we have it too full, then even the slightest bump will result in more solid material getting inside of the well. But it looks cool now. It kind of chilled a little bit. I'm gonna actually, because I'll just make sure that I'm more efficient or like more careful this time, because I don't need to show you what a mess up is anymore. So I'm gonna wrap this bad boy up again and then just be quick about letting it cool off or something, you know, if I see it boiling over. But yeah, you saw how I kind of gathered that material. I stuck my pipette through here. Unfortunately, we do have to open it, so think about the effects that that can have. I did say it smells amazing. It smells like, I don't know, it just reminds me of pumpkin pie. Maybe like some ginger snap cookies, pumpkin pie, and pumpkin pie. So I really want pumpkin pie now. Trader Joe's has some awesome pumpkins that you can just super easily make your own pumpkin pie. Did it with my son like 4 times. The best. The cool thing about this is, not sure if you ever had it. If you haven't made a homemade pumpkin pie, you probably haven't. But hot pumpkin pie, oh, you don't even know. Get out of here with that cold stuff. We want that hot stuff. But get that Trader Joe's pumpkin. Got the recipe right on there. They even got some bomb like pumpkin pie spice. It's got cloves in it, so that's why it reminded me of it. Super good. Favorite thing. Make yourself a little homemade whipped cream too. Add sugar to taste. You know what I mean? Get a little heavy whipping cream from Costco probably because it's cheaper. And then whip that up. Anybody else hungry yet? I know I am. All right, so can you see this collecting? You're not even looking at it because you're probably looking at me or probably not even paying attention anymore because I'm talking about food. We could talk about the science of food if you want. We should talk about the color changes of fall leaves. Did you guys know that, so chlorophyll, I know you know about chlorophyll, right? More like borophyll. What's that quote from? Anybody? No? Nobody? Okay. So chlorophyll is, I think it's like magnesium or something as a metal center. I don't know for sure, but chlorophyll is the like organic structure that the magnesium or the metal center, the metal is in, is called a porphyrin. And porphyrins are dope, first of all. That's what really got me into inorganic chemistry, and that's why I pursued that in my graduate school career. So, but I also loved organic chemistry, so I was doing both of those, if that seemed confusing to you at first. But I'm seeing a little bit of bumping here. So let's get that off. I'll raise this up just a little bit. All you ever really need is a little bit. All right, so let's talk about porphyrins though. So porphyrins, they got magnesium in them, right, for chlorophyll, but what about hemoglobin? Because you know that hemoglobin has a porphyrin as well, and that metal center, the iron metal center that is inside, just like the magnesium is, right? Do you guys know about blue crab blood? Something like that. Those are not a porphyrin, but they kind of look like it. So, first of all, dope, they got blue blood. Poor little guys though, because people would be snatching on them, trying to make sure pharmaceuticals are like on point, especially COVID right now, trying to make What they're trying to do? Trying to make a vaccine, and we need that blue blood to make sure that we're good. So the like those heterocyclic rings are they're nitrogen containing, and that's the general structure of a porphyrin, right? But these ones aren't connected, right? So we don't have a bunch of them connected to make one like macromolecule or like larger molecule. They're all like individual rings, I believe. So kind of cool because it's a similar structure. But the cool thing about porphyrins, the reason why I thought it was amazing is because if you just put different metal centers in there, different color, right? So we see green for chlorophyll, right? Red for hemoglobin, and then I think blue crab is either copper or cobalt or some C metal. Super cool. You can put like iridium or even different oxidation states will change the color depending on the metal, but super cool. You can add different metal centers, end up with cool, and if you crystallize it too, it looks like glitter. Got some gorgeous red or blue or purple glitter just by changing the metal center. Amazing. Inorganic chemistry is dope. Combined with organic chemistry, get out of here. Other science. Let's see. What do we got? We got some stuff here. You guys still with me? I'm trying to collect some distillate. So let's go ahead. All right, I'm gonna take this off. This is where lab is like. This is where lab hands-on skills are a little bit necessary. So what you want to do is hold on with both hands. You don't really want to set that down. Go ahead and stick that pipette in there at an angle. You can see that it is a little bit cloudy. That's because it's water and oil mixed together. We want to put that on quickly. Make sure that's nice and tight, seal. And then we've got some oil up in here and water, right? So that's pretty much what I'm going to be doing all by myself. And it smells so good though. But we need about 5 to 8 mils, and then we're going to go ahead and do an extraction with methylene chloride to extract that oil, and then we shall boil it off. But in the meantime, let's just sit tight, be patient, not rush the process. You'll find that you're like, I have 4 mils, this last part's taking forever, I want to rush through it, but don't rush through it ever, because when you rush through it, you're going to screw it up and you're going to have to start over or take a hit somewhere. You're going to take an L when you rush for sure, but let's be patient.
There was a time I met a girl of a different kind.
Jess, why do you take so long to laugh?
We ruled the world.
I don't know.
Thought I'd never lose her outside.
I worked the whole time.
We were so young. I think of her now, but then I still hear the songs reminding me of a friend.
Don't you worry, child. Jess has a plan for you. Oh, man. Don't worry about it. Back to it.
power. Minute after minute.
What you gotta know about Coolio?
Everybody's running, but half of them ain't looking.
What's going on in the kitchen?
But I don't know what's tricking. They say I got to learn,
But nobody's here to teach me.
if they can't understand,
I'm here to teach you
how
guys.
can they teach me?
I guess they can't. I guess they won't. All right, I'm going to tell you a little trick. So the goal here is to collect 5 to 8 milliliters of the oil before you move on. And so what you can do is take a centrifuge tube. I measured out. I didn't even measure it. It's about 5. So we'll pour that in here, and I'll say, hey, this is my goal when I'm isolating my oil. I need to get at least to here before I stop. Okay? And then, because these don't have measuring, there's no graduation marks on here, and so that's one way you can do it, is to determine the volume that needed. If it were more specific, then we could for sure be very careful on how much we actually measure, and we could put it on here, and we could make a little mark so it's like super precise and all good. And that's just a little lab tip for you. Okay. All right, so here's my reference, and then here's my actual substance. You can see it's a little brown because I got some solid in there because Jess was being silly. It's all good though, it doesn't matter, because really what we're going to be end up doing is, after the extractions, we're going to dry it with sodium sulfate, and then we're going to filter it. So solid material is not even a big deal. We do want to be careful, just because it's like nice to be very precise throughout the process, but if there are slight errors throughout, then it's fine if we can kind of get rid of them in the end, okay, or before the end. So, sorry. Now what we're going to do is the extractions. What we want to do is add 2 mils of methylene chloride to the extracts, the combined water oil extracts, and then we'll put that in a container, and then we will what am I saying right now? After that, we'll come, and then we'll do 2 more extractions with 1 milliliter of methylene chloride. So 2 milliliters methylene chloride first, and then 1, and then 1, and then we will dry that, and then we will boil it, separate it from the sodium sulfate, and then we will boil it down in a pre-weighed Erlenmeyer flask. Okay, the baby one. All right. I'm not going to show you the extractions just because you've seen that before, and yeah. All right, so we got our extractions in here. You can kind of see I put that sodium sulfate in there, just a small scoop. It is kind of cruising around pretty good, flowing well. You can see some of it looks like it's stuck to the walls, and that's probably because it's got the water. It's absorbing the water. And so what I'm going to do is probably hit this with the vortex. Y'all see the vortex? Let's check it out. Ooh, see this? Spinny, spin, spin. Get out of here. I'll do it. Oh, I forgot to say, the reason why I was doing that is just to make sure that sodium sulfate was mixed well, and or like kind of getting in contact with the methylene chloride. That's it. Now I'm gonna let that sit for 5 minutes. Do the extraction, or I'm sorry, filtration, and then we'll boil down our methylene chloride in I said a small Erlenmeyer flask earlier, but we're going to do a 5 ml conical vial, and so I'll come back with that mass for you in just a second. 22.263. 22.263. Write it down. Bye. Reaction's done, or the process is done. We want to let that glassware cool for a hot minute. Let's see, where's that? Where's that? Ooh, look at that. Oh. because we don't want to burn our face off, right? Burn our hands off, burn your life, whatever. I let that cool. Save this stuff. Save your foil whenever you're in lab. It adds up. Some people get crazy. They get like a real live tent, a foil trying to cover their reaction. I only use a little bit, but we want to use this. Just keep it in your drawer for the semester. All you're doing is heating stuff up with it, so it's not going to dirty or anything. But you want to make sure that you don't waste materials, right? Okay. Thanks, Mike. All right. This is some info for you right here. This is some good stuff. This is that good stuff. Write it down. Remember it. Anytime you're in a lab, right, you're doing the water in, water out situation, obviously you want to turn that water off, okay? So the water's off, okay? So now a lot of people struggle with trying to figure out this part. Where do I connect so that this water just doesn't, or disconnect so that this water doesn't just fall out everywhere? So what you can do is disconnect this portion first, because this is the bottom hose, gravity, y'all. Okay, so we're disconnecting this bottom hose from the water source. I really put it on there, so it's kind of taking a hot second. And then you can just make sure that you leave that. Oops, you can't see it, but when I did that, I lifted it up. We got some of the water came out. Okay, so now since there's no water in this area, what I can do is take this top portion off, and then now the air can flow through and force all the water down. So I just want to lift this hose up, just to make sure that no water is stuck in there and so it doesn't spill everywhere. Okay, so that's good. And now what we've got is lift this one up and the water should drain out. Okay, so I can even tilt it like that. And we're good to go. Okay, that's pretty much how you safely remove this water condenser and remove the water from that without making a mess. All right, about to do that filtration. I just want to remind you guys, I put an itty bitty piece of cotton right on top of this short stemmed pipette, and I'm taking a bigger one. I'm shoving that down. It's going down. Now, boom, not packing it too hard. Got that chilling there, ready to go. Got my pipette, and then we'll go ahead and extract that put the methylene chloride inside of this conical vial right now. Okay. All right, so we got our methylene chloride extracts with the sodium sulfate on the bottom. We've got our little filter pipette set up. Now I'm gonna go ahead and just transfer that liquid. Gravity should take care of this filtration right here. The liquid will fall right through that cotton. Once you start getting a little bit of solid on there, it might get a little bit clogged, and then it might go slower, at which point you can just use your pipette to push it through. But that's kind of why I like to get the top liquid off first, to make sure that I don't get any solid on there, and then once I get to the very bottom, I can stick it in the solid to make sure I get every last drop of that methylene chloride that I can possibly get, because that's my precious oil. Okay, and that's pretty much it. Now all we've got to do is clamp this into the water, and then it shall boil off. But, oh, sorry, I forgot about this. Put that pipette right on top of there. Squeeze that through. Remember, pop this off. Then let go of this. Okay, we're done. And let's see if we can get this as low as possible. So what I mean by that is this clamp. I want to clamp the upper portion of this conical vial, so that way I can get more of the methylene chloride inside of this water. Okay, so I'm going to first test the water with my hand, and then maybe if I feel comfortable, I'll actually leave it in there. But and you want to make sure that your water is not too hot, because remember, just a warm hug will make methylene chloride jump out of there, and you don't want to lose your oil. One thing about this boiling off of methylene chloride, remember your oil can boil off as well. If you heat it too much, because it does have a vapor pressure, it will end up leaving. And so what you want to do is kind of keep an eye on the amount of liquid you're losing, the rate. And then once that rate slows down, then you probably have just your oil. And you can also keep an eye on that viscosity as well to see. So I'm jiggling it right now just to get a sense of how viscous or not this liquid is. And once it gets lower, I will be able to tell if it's, or I'll do my best, right, to tell if the liquid is just methylene chloride, or I'm sorry, if the liquid is just the oil or if it's got a little methylene chloride in there. Okay, so it's a little tricky, but just do your best. All right, if you look at the top of that conical vial, you can see it looks like something's moving in there, right? Oh, there you go, perfect. That's the vapors leaving. And so you can use this as a guide as well. Once that kind of slows down, you're probably good in terms of removing methylene chloride, okay? Okay, not much left, but you can see it. Ooh, smells. Ooh, smells so good. Let's weigh it now. I'm just gonna take you with me. Just gonna take you with me. See how dark it is out there now? I've been here for a minute, and I got this drop. Science. So 22.312. Wait, oh, it went down. 22.31. Oh, you don't take that away from me. 20. Let's go with 22.312, because that's what I saw first, and it kind of equilibrated there for a minute. Yeah. Here we go. This is the IR. Just put a drop on here. I'll show you right quick. Put a drop on this disc and then put it in here, and there you go. That's what we got. I'll provide that to you so you get to do all of the analysis. Okay, bye.